Hey everyone, this video is to help study for the Unit 4 test coming up. Just a reminder, this is a guide, it's not all inclusive, so just make sure you're looking at some of your other classwork activities, your class notes. Everything is on Google Classroom, as well as the answer key folder that you have access to in Google Classroom as well. So just use this as a guide, but I'll just go through some of the most important things that you need to know. So the first thing we learned in this unit was molar mass, what you do to calculate the molar mass. If you look at the example, if you have something like magnesium sulfate, you have 1 magnesium, 1 sulfur, 4 oxygen. You just take the masses of those and multiply them by the quantities of each and add them up. So the unit for molar mass is going to be grams per mole. You can see the math here that magnesium sulfate, which is MgSO4, has a molar mass of 120.36. Now on the test, I'm going to give you molar masses for some of the stoichiometry problems and things like that, but if asked in a multiple choice, you will need a periodic table to figure out the molar mass of the individual substance. Okay, the next thing we went over was mass to mole conversions, so just taking the mass of a substance and converting to the moles of that substance. So you're going to start with your given, and then what you're going to end up doing is dividing by the molar mass. So remember, the units for molar mass are grams per mole, but you can invert them depending on the way that you need your conversion to work out. So if you start with grams, divide by the molar mass, then you're going to be left up with how many moles there are in that substance. Just talking about the Kool-Aid lab real quick, because this was on one of the quizzes and it tripped some of you guys up. So molar mass, again, is used to do all of these types of conversions, especially when you're starting with mass, but also when you're ending with mass. If you're given a molarity problem, which I'll talk about molarity in a second, you might be expected to figure out what the mass of that substance is, because if you find the number of moles, like in this problem here, you can then find the mass by multiplying by the molar mass. So just keep that in mind. I'll talk about molarity, like I said, in a second, because our equation is moles per liter, so would be the moles of the solute over how many liters of the solvent you have, or the total volume of the solution. But you might be expected to recall the Kool-Aid lab, just because you might be asked for moles or you might be asked for mass. But remember, if you know moles, you also know mass that's related through the molar mass. Okay, so more on molarity here. Molarity is M, capital M. You can just write M or give me the units moles per liter. It's the same. Remember, capital M is like a combo unit, so it combines that moles per liter unit and just puts it as an M. It makes it a little bit easier to write. You have to convert to liters. So if there's a problem and I give you milliliters on the test, just remember that molarity is given moles per liter. It's not moles per milliliter, so you need to use that conversion. So if you're given the mass, you can calculate the molarity. If you're given the moles, you can calculate the molarity. What you need is the moles and the liters, which is the volume. But remember, if you have mass, you have moles, and if you have moles, you have mass, because it's related through that molar mass, which is the standard. So you can go and look at some of these problems. Like I said, the answer key is linked. Percent composition. This we did a lab on when we dehydrated the hydrate, and then you also have these problems. There's definitely going to be a problem like this. So you're taking the percentage part of a whole, so whatever the part of the compound is I'm looking for, over the whole molar mass. And again, this is based in molar masses, so you might need the periodic table to figure out those individual molar masses. But if we look at the first one, copper bromide, copper 2 bromide, it's asking you for how much of it is copper, like what percent by mass is copper and what percent by mass is bromine. The key factor here is that when we talk about bromine, there's 2 of them in the structure. So this number here reflects the mass of 2 bromines. And the molar mass on the bottom, of course, is the molar mass of copper 2 bromide, so it's the mass of the whole thing. Again, remember, part of a whole, and I know you have that equation in your notes. Mole to mole stoichiometry, this was the first time we used the foldable. So remember, mole ratio is the ratio between 2 substances in a chemical reaction, and that's given by the coefficients. So the big thing there, you need a balanced equation to get your coefficients. So in this problem here, we started with 2 moles of nitrogen, that was our given, and we know that we can get to moles of hydrogen through this mole ratio. So the 3 from or the 3 moles of H2 comes from the fact that there's a 3 in front of the H2 for the coefficient, and there's no coefficient in front of N2, so we just assume that it's a 1. That's how that works. And again, you have access to this. You can go through some of them yourself, but this is mole to mole, especially when, well, not especially, it is when you're going between moles of one substance to moles of another substance. Then we talked about mass to mass stoichiometry, which was the first time we used the foldable in its full effect. So you have really 4 fractions there, so 3 steps. When you're going from mass to mass, you need to convert to moles of the first substance, then convert to moles of the unknown substance, and then finally the mass of the unknown substance. You get it the same way. So if we just go through this example that you're given, you divide by the molar mass to get moles of H2. Then you use the mole ratio to get it in terms of moles of N2, and then you multiply by the molar mass of N2 to figure out what that final value is going to be. Remember, this step was just what we talked about at the mole ratio step, which comes from the balanced chemical equation. All right, then we kind of threw a bunch of stuff in. So you have liters and atoms conversions. Remember Avogadro's number, 6.02 times 10 to the 23rd. That's your conversion for anything that is atoms, particles, molecules, formula units, and then you might even see something called representative particles. Remember scientific notation, depending on what calculator you have, if you get an answer, it might say E. If it says E, E stands for times 10. So you could write Avogadro's number like this. And that's the same thing as saying 6.02 times 10 to the 23rd. Just keep that in mind, but this works the same way. You have to figure out what your given is and then go to what your unknown is. So in this case, the given was in terms of mass, and you're looking for atoms of a different substance. So your first conversion to get to moles, then the mole ratio, and then your conversion to get to whatever unit the question's asking you for. Limiting an excess reactants was a new concept, but it was still stoichiometry. The big thing here is just problem solving. So if you're looking for your limiting reactant is the one that produces the lesser amount of product, and your excess is the one that produces more of the product that you're looking for. So the key here, if we look at this first problem, is that you're solving for the same substance. So we could, in this problem, we solved for copper, but we could have also solved for aluminum chloride. We would have gotten, a different quantity because it's a different chemical, but your analysis at the end would have been the same. So since copper chloride or copper 2 chloride produced the lower amount of copper, that was our limiting here. And then aluminum produced a higher amount, so aluminum was our excess. These problems are just stoichiometry problems with one extra layer of analysis, so just know the vocab for limiting and excess, which should be in your notes. So limiting produces the lower amount, excess produces the higher amount. Then we got to percent yield, which was similar to the lab with the vinegar and baking soda that we did, because you had to identify what the limiting reactant was and then use that to calculate your percent yield. There's the bell. So percent yield is what a scientist actually got in the lab, like experimental value, over what you should have got in theory, which is stoichiometry. You just see some of these examples up here. For number 1, this was just working through the equation. So the scientist yielded 4.5 grams in the lab, or produced 4.5 grams, but you should have gotten 10.7 grams through the stoichiometry, which is what you should have gotten on paper. And when you do that math, it comes out to be 42.06%. Then for a problem like this, which is going to be more similar to something you might see on the test, you have to do the stoichiometry to figure out how much that theoretical yield is going to be. So this one, it's a mass to mass, so grams of magnesium to grams of hydrogen. You figure out what you should have gotten mathematically. So remember, what you should have gotten mathematically is always going to be your theoretical, and then the number that they give you as what's produced in the lab, that's going to be what you're looking for your actual yield there. Then we started talking about acids and bases, and I'm going to go to the pH lab first. Indicators are things that indicate the amount of hydrogen that are in that solution, because we know that pH is the concentration of hydrogen. So we used cabbage juice to predict the pH of some household solutions, and then you all went through and used the sensor to figure out how what the actual pH is, and then we just talked about the benefits of both. So indicators are normally relatively cheap, but they're not super accurate, but pH sensors are much more expensive, but they do give you that level of accuracy. Then for acids and base theories, we learned about strong versus weak acids. So strong acids break apart completely, and they give off H plus in solution, but weak acids, like the ones on the bottom, break apart but only slightly. Similar with bases, strong bases break apart completely, weak bases break apart but just a little bit, and then they all give off OH in solution. And then things that are neutral don't have either H or OH in solution. And water is considered neutral because unless you do something to it, it's not going to have OH or OH in solution there. So that's why you get a neutral pH. Before we get there, we're going to talk about neutralization reactions in class as well. So a strong acid plus a strong base is going to produce a salt and water. You can look at that example there, but really with neutralization, the important thing is that when you have a strong acid and a strong base and you mix them together, the concentration of H plus and the concentration of OH are going to offset each other. Because there's not going to be any left in solution. They're all going to get combined to make just water, which is going to give you a pH really close to 7, which is kind of cool. And this is what we did in the vinegar and baking soda lab, if you remember the pH data you took. So we started with vinegar that had a pH around 2, and we ended with the pH was a little bit higher. It was like pH of 8 because there was excess baking soda. Baking soda is a base, so of course it's going to drive the pH more basic, but if we had calculated the neutralization to be complete, we would have gotten the pH around 7, but the point of that lab was to figure out what the limiting reactant was. Then dilutions, this is the last thing we're going to talk about. You have your dilution equation, and it's a dilution equation, but you can really use it for making things more concentrated too, because what it comes down to is a ratio. So if you have your initial concentration, your initial volume, and then your final concentration, final volume. Again, most of the time this is used for dilution, but you'll see a problem where it's evaporating, and if you do it backwards, it ends up being a dilution, but you can do it forward and backwards. As long as you keep your initial conditions initial and your final conditions final, then you'll get the answer that you want. Also, something to make note of with the dilution equation is that it doesn't matter if you use milliliters or liters for your volume, but it has to be consistent. So if the problem gives you milliliters, your answer should be in milliliters. And if the problem gives you two different volumes, you need to convert so that they're equal, because then it's not going to work out mathematically. Just a few different types of problems here. If you're solving for an unknown, great. It's easy, just plug it in. But for a problem like number 5, it asks you how much water you need to add. So just be careful about what the question's asking you for, because if you just give me V2 in this problem, that's not going to get you full credit, because the final volume is 1,200 milliliters, but it's asking you how much you need to add. So if you're starting with 500 milliliters, you only need to add 700 milliliters to that. Okay, I hope this was helpful. As you can see, we did cover a lot throughout this unit. But open notes, make sure you have as many notes as possible. You can copy down some practice problems, and if you have any questions, let me know. But thanks for watching, and good luck on the test.